Now, how collider actually looks like. So, this is one of the basic schematic of intersecting storage ring. This was the first hadron collider and it was operated in the sun. Actually, we can see that from the proton synchrotron, beam is sending here and proton synchrotron also beam is sending here. So there are two rings, one in green color and one in a positive. Two are independent rings, completely different accelerators are there. And at these points, these two accelerator vacuum chamber crosses each other. So at these locations, collision takes place. And at these locations, detectors can be put to detect these collisions. There may be another type of schematic like we have in Large Hadron Collider at Sun. Here in the same vacuum pipe, both the beams are rotating. And that's why its dipole looks like this. These are the coils around the dipole and there are two chambers. One is for the first beam and another one is for the second beam. So both the beams are kept into the same chamber. And then at certain locations collision are taking place. Only energy is not sufficient for the colliders. Actually, when we hit this fixed target, in fixed target there is a plenty of molecules or atoms or particles are available because fixed target is high density material. But beam is not so dense. So number of events means number of collision events reduces. So there is another important factor which is very useful, that is related to the how much events are taking place in per second. And definitely for a particular event, this rate, how much event are taking place, depends on scattering cross section for that particular event. Suppose we want to pinpoint some or pick some event, then what is the scattering cross section for that event? So that describes what is the event per second for that particular type of thing. So there is proportionality constant L, which is known as luminosity in the case of colliders. So in colliders, luminosity has to be increased. If we have very high luminosity in this case, so even with a smaller cross section of the events, we get sufficient rate of events. And if we get sufficient rate of events, that events can be detected. Because detectors cannot detect events if these are very, very rare. So for reaching the detection limit, dr by dt has to be increased. So this luminosity has to be increased. Like in the case of synchrotron radiation sources, we have seen that emittance has to be reduced. In case of spallation neutron source, we have seen that beam power has to be increased. And in the case of colliders, luminosity has to be increased. So what is luminosity? Now we see that. Suppose there is a target. Right now we are taking fixed targets. So there is a beam which is going on this target. We take flux of this beam. Flux of this beam means number of particles per second as the phi. And the density of the target material is rho target. And we are considering that this rho density is same throughout the target, means target is homogeneous. And target's dimensions are much larger than the beam diameter. Now the length traveled by the beam in 1 second in the target, take it is to be L. This L is the length taken by the beam in 1 second. Now if cross section of the scattering is sigma, Suppose we are interested in some event and that has scattering cross section sigma, then total possible interaction in 1 second will be rho target. Means this, suppose a single particle is passing through this target, a single particle is passing through the target, means it will interact with up to L length, L into sigma, sigma is the scattering cross section, into rho, sigma L, sigma is the scattering cross section, means it is area, and L is the length, and rho is the target material's density. So total number of particles in the target in the path of this particle will be rho into L into sigma. Now if we are taking beam's cross section as A, so if for one particle it is rho L sigma, so for whole beam will be rho L sigma multiplied by the area of the beam. So many interactions are possible with sigma cross section. Now for per unit time in per unit area, we will have phi rho target L sigma from this we will get this. Now here you can see that this sigma means dr by dt is equal to L sigma. So apart from this sigma, this whole things define the luminosity of the collider. So luminosity of the collider, a collision experiment, I will not say collider because we have taken the fixed target. So in this fixed target experiment, what is the flux of the beam, what is the density of the target, and what is the length covered by beam in 1 second. That defines the total luminosity. In case of target, in case of colliding beam, this target is also moving and rho is not so high. So we have to take the density of both the beams. And now if we will take density of both the beams, means luminosity depends on density distribution of the beam. It is highly depending on that. So now I will depend on the distribution function, how the density is there. So we can obtain from, as of the previous line, total overlap integral of these two bunches. What is the overlap integral? So overlap integral will be according to density. What is the density of this first bunch? What is the density of this second bunch? And we can integrate on x, y, z and t because these are moving bunches. So we have to integrate on time also. And time has been changed as per in our accelerator ds0. So we have changed time from t to ds by beta. So these integral will show how much events can take place with particular cross section sigma. This k here defines some kinematic coefficient because bunch are moving. So when we solve this, we will get rho 1x as x because density there may be a distribution function of the density in this bunch. There may be a distribution function in the perpendicular direction also. So this is rho 1y, and along the s also there may be a distribution function. So that is rho 1s minus sv because it is moving along the s-axis. So in case of s we are getting s minus sv, and similar distribution for the second bunch. In case of second bunch, there will be s plus sb because it is moving in the opposite direction to the first bunch, and again integrate. So this will give you the total overlap of densities, distribution function. And if we multiply by number of particles in bunches, we get total events. This is the distribution function multiplied by number of the particles, then we get the total events. Now if there are n b bunches, this is for one bunch, how many particles are there in the first bunch how many particles are there in the second bunch, and many bunches may be there. So this is the number of bunches in, and this is the revolution frequency, means in one revolution frequency how many bunches are there. So this completely defines what is the luminosity of the collider. So this number has to be increased for the collider. Now you can see that this highly depends on the distribution function, density distribution function of the bunch. So in most of the cases, analytical solution will not be available and numerical integration has to be taken place. But for a simple case, Gaussian distribution, we can calculate it. So take bunch as a Gaussian distribution. It is a Gaussian distribution. I have written here only for the case of S. Similar distribution, Gaussian distribution will be in X and Y also. Means in X also it is a Gaussian distributed beam. In Y also particles has Gaussian distribution, and in S also particle have Gaussian distribution. So Gaussian distribution is defined as exponential of minus S by 2 sigma squared. Sigma is the standard deviation of this distribution. So when we will put at the place of rho 1x, rho 1y and rho 1s, and here in this case we are considering same beam, same bunch on the both side. So second bunch will also have e raised to minus x square upon 2 sigma s square. That's why this 2 has been omitted here, because both are having the same. So e, for the first bunch we are having e raised to minus x square by sigma 2 sigma square. For second bunch also we are having e raised to minus x square by 2 sigma square. So for it will become e raised to minus x square sigma x square. Similarly in the y case, similarly in the s case. And this sigma s root 2 pi makes this denominator. Now if we integrate e raised to minus at square from minus infinite to plus infinite, the integration is root pi by a. Using that relation, we get finally the luminosity in this case. Now you can see that in the case of Gaussian bunches, luminosity can be increased if number of particles per bunches can be increased, if number of bunches can be increased, and beam sizes has to be reduced. Means very small beam should be there when the collision is taking place, and a very large populated bunch should be there. It is from the common sense also. If we are densely packed the bunch, number of collision events will be increased. Means very large number of particles, if it is packed into a very tiny bunch, then definitely if these bunches will be collide, collision events will be increased. So this is the same thing we are saying mathematically. But there are some problem. Actually luminosity decreases in the practical cases because we were considering as head-on collision. In accelerator, beam comes at certain angles. First beam is coming through this direction and second beam is coming through this direction. So this angle actually reduces the overlap integral. In the case of head-on collision, overlap may be complete. This will come here, this will come here, and at certain event they may completely overlap. But in the case of angled beam, complete overlap will not be there. So overlap integral will be reduced. Or we can say in another language that effective beam size has been reduced. So this is the reduction in the beam size, and this theta is there. This is the theta. This theta is here. So by crossing angle, actually luminosity decreases. So whatever we have calculated, that is the maximum luminosity. In actual collider, this will be decreased due to crossing. There are many more effects which will decrease the luminosity in particular collider. The one is hourglass effect. What is hourglass effect? Hourglass effect is like this. Suppose this is the S, and suppose this is the collision point. So I want focused beam here. Means twist parameter beta will be minimum here at this location. So suppose this is the twist parameter beta. So it goes like this. It means sigma here at this location S is equal to S2, or sigma here at this location S is equal to S1 are different. Means sigma or beam size actually in collider is a function of S, and we have not taken that. We have taken the constant sigma throughout the S. So in fact sigma changes with S, and again this reduces the overlap integral. And if you want to make beam size more focused, means if we reduce the beta more, then beta will go like this in the drift space on the both side. So if we squeeze the beta, hourglass effect increases. Means sigma as a function of S has stronger dependence if we want to squeeze the beam more and more. So there may be an offset also. Offset means due to imperfections. Actually no machine is perfect. We have studied the perfect machines, means perfect dipole, perfect quadrupole, beam is also perfect, and these are nicely aligned along the design axis. In real, actually there may be imperfections in the dipole magnets during manufacturing or fabrication, in the quadrupole also. During placement there may be a misalignment also. So these things deteriorates the parameters which we have evaluated. So in that case this luminosity will also be decreased. So those all are effects which decreases the luminosity, and one has to control so that luminosity should not decrease much. Otherwise rate of events will be decreased. So these are some of the list of colliders in the world. Mostly there are circular colliders. You can see this list is circular. Only one collider, SLC, is linear accelerator based collider. Now we have studied during the synchrotron radiation chapter that when electron is subjected to some acceleration, it radiates. So pushing the electrons to very high energy in circular accelerator is not possible. Maximum energy achieved for electrons in circular accelerator is 100 GeV. That was in large electron positron collider. That was in the same tunnel where the presently large hadron collider is situated. So beyond that, as we increase the energies, emission of synchrotron radiation becomes enormous, and the requirement of RF power becomes impractical. So future collider in case of leptons should be made linear. However, for hadrons, for heavy particles, circular colliders can be made. Now in the case of hadron, hadrons are composite particles, means proton itself has 3 quarks. This is not a fundamental particle. Proton is not the fundamental. This is a composite particle. And if hadron collision is taking place, this becomes very complex because we are colliding two composite particles. So there may be a large number of events, and to pinpoint some particular event is just like to search the needle in the hay. So that's why hadron colliders are known as discovery machines. But leptons, electron positrons, are fundamental particles. These particles do not have any internal structure with them. These are fundamental. So far, these are fundamental. So their collision is clean collision. So by tuning the energy of electron and positron, the rate of event of particular collision can be increased. So these are precision machines. Lepton colliders are the precision machine, hadron colliders are the discovery machine. However, lepton colliders cannot be built using the circular accelerator. And if we are going to build with linear accelerators, the length becomes enormous. I will give you an example. There is a project plan for the International Linear Collider for electrons and positrons. and in that collider the maximum energy, which is nearly 1 TeV per beam, and the length of that collider is going to be 40 kilometers. So linear colliders are big. So there is a way to get rid of this. Instead of electron positron or proton colliders, make the muon colliders. Muons are leptons. These are fundamental. These particles do not have internal structures, so these are fundamental. Muons are fundamental. However, muons are 200 times heavier than electrons, so it radiates less. So we have lepton but less radiation. So we can make circular accelerators which can push the muons to very high energies. So there is also plan in US to build a muon collider. Tevatron now has been closed when LHC was started its operation. Hera is the only collider which collides electron and proton. And in this course, now I will give you very short summary that we have seen that different kinds of cyclic accelerators, and in cyclic accelerators the basic condition is to maintain the synchronism, and how we are achieving the synchronism on the basis of that different accelerators are categorized. So cyclotron, in this accelerator revolution time is independent of the particles energy. However, this can handle only heavy particles, because for the light particles gamma changes rapidly and synchronism picks up. So for electrons we can accelerate in a tiny accelerator microtron, where the synchronism condition is achieved differently. Then there are synchrotrons in which orbit is kept constant, and the problem of large magnets of cyclotron can be solved, because on that constant orbit we have to put the magnets only. And when we analyze the synchrotron or motion in the synchrotron, we obtain the Hill's equation, and that Hill's equation can be solved in two different ways. Both are leading to same solution. One is the matrix method and other one is the parameterization of the optics. In that we got three parameters, alpha, beta, gamma, which is named as twist parameters, and an important parameter, emittance. And then we saw that how off momentum particles can be analyzed or their motion can be analyzed. The solution of Hill's motion gives you betatron oscillations, and an off momentum particle with that betatron oscillations, there is a dispersion term. In longitudinal plane, RF cavity works as the focusing element that keeps the particles focused in the longitudinal direction also, and therefore synchrotron oscillations are there in the longitudinal plane. Then we saw three types of different accelerator, namely synchrotron radiation sources, proton synchrotron for spallation sources, and a little bit of colliders. In these three accelerators, we picked one particular parameter in the lecture, and we concentrated our lecture around that particular parameter. For the synchrotron radiation sources, we picked that parameter, that what is the radiation damping and quantum excitation, and how we can define the beam emittance using that. Why we picked that parameter? Because beam emittance is the most important parameter, and whole design of synchrotron radiation sources or efforts in design go for lowering down these beam emittance. There are many more things in the synchrotron radiation sources that cannot be covered in this lecture. And also in the case of proton machine, we mostly concentrated towards how we can define the beam power and how it is different from the electron machine. And we picked only one aspect again here, that was the space charge. A very simple picture was drawn by taking the uniform beam for space charge calculation, and we saw that betatron tune has been changed in the presence of space charge, and this space charge can cause the beam growth and beam loss can occur. So these one important parameters was picked for this lecture. There are many more parameters, but anyhow in the limited time we cannot cover all these things. And in the case of collider, we again picked a single parameter, that is luminosity, and what was that luminosity we understood now. So in this case, I complete this cyclic accelerator course.